All right, guys. So this section is a little bit harder than I remembered it being the last time I taught this class. Don't worry now. We got a nice, relaxing video to do some extra problems to help you succeed. And as a reminder, please email me and talk to me if you have questions, because this stuff is not easy. Okay, so we're going to start with number 8 in the textbook. Why am I smiling? I'm sorry. It's hard, but I'm here to help you through it. Seriously. So use equation 3.1. And again, if you're curious about what that is, you can click on it. The book will take you right towards equation 3.1. So this is one of the first formulas that we used. Difference quotient, average rate of change, slope of the secant line. That first video, that was a good time compared to that fourth video. Use that equation to find the slope of the secant line between the two values for the function. So we already done this. This is the same as before in an earlier section. Okay, so our function in number 8 is f of x equals the square root of x minus 9. And we're looking specifically between 10 and 13. All right, so x is going to be the second one, and a is going to be that first one. We always do second minus first, almost always. All right, so in our formula, right, our formula is q equals f of x minus f of a, all over x minus a. That's that difference quotient formula. The bigger one is usually x, which goes first. Smaller one is going to be a. So it might be useful, right? What is f of a? F of a is f of 10. Plug in 10 here. Plug in 10 here, you get the square root of 1, which is 1. And again here, if you plug in x equals 13, you're going to get the square root of 4, which is 2. And now you can just plug all this stuff in and get your answer. We found that f at that x value is 2, minus f at that a value is 1, divided by our x value, we said was 13, minus the a value, which was 10. Simplify, you get 1/3 is our average rate of change. The slope of this secant line is 1/3. Let's visualize that. Let's connect all of the dots. Ooh, let's not remember this one. This is the function square root of x minus 9. Maybe let's go back to some normal scale. Square root of x minus 9. And we're looking at the slope of the secant line between 10 and 13. The slope of the secant line between 10, 1 and 13, 2. Remember, secant line is just the line between these 2 points, which is y minus the y value equals the slope. We found the slope to be 1/3 times x minus the x value. So you can see here this pink thing, it's not a tangent line, right? Pink is not a tangent line. It crosses at both points. It's the secant line. And as these 2 points get closer and closer together, the secant line becomes the tangent line as these points get close. So that's how it all ties together. But the actual answer is the slope of the secant line is 1/3. Let's do 16. All right, find the slope of the tangent line with equation 3.4. Which one is that it wants us to use? Ah, the one with h's. Find the slope of the tangent line with the h one. Slope of the tangent line is the derivative at that point. And find the equation of the tangent line as well for 16. F of x equals the square root of x plus h. I wanted to do more square root ones because we didn't do a lot of that in the other videos. All right, so the derivative at 1, that's the same as the slope of our tangent line. And it uses the formula, the limit as h goes to 0. of f of a plus h minus f of a all over h. Okay, now we plug things in. So as a side note, a is 1, so f of a plus h, that's f of 1 plus h, which means look at this function and replace all the x's with 1 plus h's. That's the square root of 9 plus h. So we use that. That is f of a plus h, so we replace it. They are equal to each other. We can replace one with the other. What was f of a? A was 1, so this is going to be f evaluated at 1. Plug 1 into this function. That's the square root of 9, which is 3. We can't use direct substitution. Have to remember our limit procedures, our limit methods from chapter 2. For square roots, we multiply by the conjugate. The square root of 9 plus h plus 3 divided by the square root of 9 plus h minus 3. This is how we did it in chapter 2. We had a couple examples like this. So feel free to go back and review those if you don't remember. Now the top, we could either FOIL it out or use the difference of squares formula. The difference of squares formula says that if I have a minus b times a plus b, so notice how these two things are basically the same. Just one's a minus sign and one's a plus sign. That's going to be the first thing squared. You square a square root, it cancels. You just have 9 plus h. Minus the second thing squared. 3 squared is 9. You could also FOIL this out and simplify. In our denominator, we're going to leave this factored. A lot of times it's easier if we leave denominators factor. Plus 9 minus 9 cancels out, and we get something really nice. Well, relatively nice. I was actually talking to another friend as I go on a little further in this problem. I was talking to another friend who teaches calculus, and I actually think she teaches a much harder calculus than I do. And so I'm thinking that this is a hard section, but I guess it could be worse. All right, so once we get the cancellation, we can now use direct substitution. Uh-oh. Oh, do you see my mistake? We can't use direct substitution here because if we plug that in, we're going to get 0 in the denominator, which shouldn't happen. This is where the mistake is. Anytime we multiply by something, we need to make sure we multiply by the same thing on the top and the bottom. Otherwise, we're changing the problem. So now we can use direct substitution. Plugging in h equals 0 is going to give us something that's defined. So we get the square root of 9 plus 3 on that denominator, which is 3 plus 3, or we get a slope of 1/6. The derivative is the slope of the function here. It's the slope of the tangent line too. It's about 1/6. That's how the function is changing. The instantaneous rate of change is about 1/6. That's our answer to part A. Find the slope of the tangent line. We did it. Now part B, find the equation of the tangent line. It's going to be y minus the y coordinate. The y coordinate's 3. That's the function value at this point. Equals the slope, 1/6, times x minus the x coordinate. This is point slope form. The x coordinate is our a value of 1. So if we plot this, we should see a nice tangent line. All right, so if we look at the square root of, I already forgot our function. Square root of x plus 8. And our tangent line is y minus 3 equals our slope. times x minus our a value, which is 1, we should have a nice tangent line at x equals 1. Indeed, we do have that nice orange tangent line skipping off the graph at 1. It doesn't actually cross here. This is the y-intercept, so don't be misled. It is only touching at 1 point. All right, so we found the slope of the tangent line. We found the equation of the tangent line. Problem number 16 is completed. Here's 28. For the following functions, find f prime of a using 3.5. Which one was that? Find the derivative. Okay, find the derivative using the formula that doesn't have the h. 28 is looking at this function, 1 over x minus 3, and an a value of -1. So the derivative, that's the slope of the tangent line, which is the slope of the secant line as the 2 points in the secant line get really close together. So it's the slope of the secant line as that second point gets really close to that first point, as our x value gets really close to -1. That's going to be f of x minus f of -1 divided by x minus -1. Be very careful with your negatives here. So f of x, we already have that. Is the limit as x approaches 1 of f of x, which is 1 over x minus 3, minus f of -1. Let's go off to the side to find that. Plug -1 into our function. That's 1 over -4, or -1/4. So we're subtracting a negative. That's the same as adding a positive. Same with the denominator. This becomes x plus 1. And again, we have complex fractions. Little fractions inside of big fractions. We simplify complex fractions by multiplying by the LCD, 4 times x minus 3, divided by 4 times x minus 3. Let's distribute. On the bottom, we're just going to leave it factored. So we get the limit as x approaches 1, 4 times x minus 3 divided by x minus 3, plus 4 times x minus 3 divided by 4. Multiplying fractions is multiplying the tops together and multiplying the bottoms together. In the bottom, we're going to have x plus 1 times 4 times x minus 3. And we get some cancellation. There should always be cancellation when we simplify complex fractions. We should always get rid of the little fractions when we simplify complex fractions. Just left with 4 plus x minus 3. On the bottom is 4 times x plus 1 times x minus 3. So we're getting close. Let's just simplify the top a little bit. Limit as x goes to 1. 4 minus 3 is 1. We get x plus 1 on the top. Bottom is 4 times x plus 1, x minus 3. Ah, very nice. The top has a factor of x plus 1. The bottom has a factor of x plus 1. And we're almost done. 1 over 4 times x minus 3. We can now use direct substitution. This limit is 1 over 4 times -2. Or about -1/8. That's the slope of our tangent line right here. And again, you should always be able to check. Let's graph this function, 1 over x minus 3. Let's graph our tangent line, y minus the y-coordinate. We said the y-coordinate, that's in red on the top, was -1/4. Y minus -1/4 equals the slope, which was -1/8, times x minus the x-coordinate, was -1. At -1, That's where we have this tangent line. Oh, wait, this doesn't look like a tangent line. Am I looking at the right thing? Hold on. Did I make a mistake? An a value of -1. Yeah. So it's a good thing we checked our answer, because notice this orange is not a tangent line. This orange is crossing at multiple places. So let's see what happened. Function is 1 over x minus 3. Function value is -1/4. That is right. The function value is -1/4. I typed it in right, I believe. But I think we evaluated it. I made a mistake finding our slope. So let's go back and check our work. The denominator should be x minus the x coordinate. And again, this is why I recommend you check your work, because even when I do this, sometimes I also make mistakes. Just going to skim through this really quickly. If there's something obvious. Oh, I see it. It's a very simple mistake. Easy to fix. Something's going on here. Jason, you dropped your negative. This is as x approaches -1. So we can now use direct substitution for -1. We get -1 minus 3 is -4. And we get 1 over 16 negative. Check your answers. All right. I'd like to lie to you guys and say, yeah, I make these mistakes on purpose to show that it's important to check your answers, but I don't. But honestly, this is why we check our answers. So let's change that slope to -1/16 and see if we have a tangent line now. Oh, that looks good. Yeah. Nice. Look at this. That's a tangent line. That right there is a tangent line. Let's do some more. Or was that the end of 28? Yeah, 28 only wanted us to find the slope. I graphed the tangent line because that's a good way to check our answer, and it's quick. Let's do 32. So now with 32 in the homework, I'm not having you, so there's a big table that you're supposed to fill in. I'm not having you do all this table. The table is just for us to explore. Okay? So what it wants us to do here, let me remember. Find the slope of all of these secant lines. So let's find these slopes, but we don't have to copy it down. I'm not making you write it down. I don't want it to be tedious. But how do we find the slope of all these secant lines? We're looking at the point 0, -1. So let's remember the formula for the slope of a secant line. The slope of the secant line, sometimes we use the word q, is going to be f of x minus f of a all over x minus a, where a is the point that we care about. So a is 0, and the function value at 0 is -1. A is 0, f of a is -1. So this is going to be f of x minus f of a, which is -1. Subtract a -1 is plusing a 1, divided by x minus 0, like so. So to fill in this table, and again, you don't have to write it down. I just want you to see what's happening. To fill in this table, let's just plug this in to Desmos and then use different values of x's. So our function is x plus 1 over x squared minus 1. X plus 1 divided by x squared minus 1. So let's look at this function value at a bunch of different points, add 1, and then divide by that function value. So 0.1, for example. Oops. And as we get closer and closer to 0, look what happens to our average slope. We're at negative 1.1. Now negative 1.01. Now negative 1.001. Negative 1.0001. What's happening? The more and more zeros I add, what's happening to our slope of our secant line? The closer we get to 0 from the right, the slope of this secant line is approaching negative 1. So as x approaches 0 from the right, slope of that secant line is approaching negative 1. Let's check the other direction. Let's look at what happens if we're a little bit below 0, like negative 0.1. Then we have negative 0.9 at a 0, negative 0.99, 0.999, negative 0.09, sorry, negative 0.9999. And you can see that the more and more zeros that we add, the closer it gets to negative 1 from the other direction as well. So it's approaching negative 1 from the left and from the right. So the slope of that secant line is approaching negative 1. So we found all these slopes. I'm not making you write down every single one. Estimate the value of the slope of the tangent line. Well, if the secant line has a slope that's approximating negative 1, then in part B we'll say the slope of the tangent line seems to be negative 1. This is not a proof. We're using tables. We haven't calculated that this limit equals negative 1. We're saying it looks this way. Find an equation of the tangent line at that point. Y minus the y value, which is negative 1, equals the slope times x minus the x value, which is 0. Let's plot this along with our function and see if we've got a tangent line on our hands. Y plus 1 equals negative 1 times x. Oh, that green graph, that green line, sure looks a heck of a lot like a tangent line to me. It's a tangent line at the point 0, negative 1, which is what we wanted. Checking our answer is great. Make sure we did it right. And it helps us know what things look like. All right. Let's do our last problem of this video. Number 42. Use the limit definition of the derivative to show that the derivative does not exist at this point for that function. F of x equals x to the 2/3, which, as a side note, that's the cubed root of x. Sorry. This is actually important. Wait. No, it's not actually important. It's the cubed root of x squared. Remember, rational exponents are radicals. And we're looking at the point at x equals 0. So it said use the limit definition of the derivative to show this limit doesn't exist. To show the derivative doesn't exist, right? We want to show that the derivative doesn't exist. So let's find the derivative and show it doesn't exist. The derivative at 0 is the limit. There's two definitions you can use. Either one's fine. As x goes to 0, f of x minus f of 0 divided by x minus 0. Let's simplify. Limit as x goes to 0. The function, which is x to the 2/3. When you plug in 0, what do you get? It's a cubed root of 0 squared. It's a cubed root of 0. The cubed root of 0 is 0. Now let's simplify some more. We can't use direct substitution yet. This is x to the 2/3 divided by x. I'm going to rewrite the denominator as x to the 3/3. Because x is the same as x to the first power. And 1 is the same as 3/3. Why do I do it this way? You don't have to. But remember, when simplifying the quotient of monomials, one monomial divided by another, you just subtract the exponents. This is x to the negative 1/3. Remember what negative exponents are. Negative exponents just mean reciprocal. And if you wanted, you could rewrite this a little bit more. You don't have to do this last step. This is what the derivative is going to be. The problem is that this doesn't exist. Right? What's happening as x goes to 0 here? As x goes to 0, from the right, we're getting a really, really big positive number. And from the left, we're getting a really, really negative number. So specifically, we could say, well, the limit as x goes to 0 from the right of 1 over a cubed root of x is equal to positive infinity. And that tells us immediately that the limit doesn't exist. Remember, when we say the limit equals infinity, the limit technically doesn't exist. We just describe the behavior by writing infinity. It's going to infinity from the right, negative infinity on the left. This limit does not exist. And we can look at this graphically with two different ways. First, let's look at this. Let's see how this function behaves near 0. 1 over the cubed root of x. Look how this function behaves near 0. From the right, shoots off to positive infinity, and from the left, it shoots off to negative infinity. This limit at 0 does not exist. This is an infinite discontinuity. It's not continuous, it doesn't even exist. And the limits go off to infinity or negative infinity. This limit definitely doesn't exist because we can look at the graph. Now let's look at the original function and see why the derivative does not exist. So this is what the limit function looked like. Let's look at the original function and look at the derivative. I'm asking about the slope at this point. This is what's known as a cusp. What's the slope at this point? Well, we can't know this. And we can approximate this with secant lines. But the limit, as these secant lines get really, really close to 0, doesn't exist. And I think I can show this. Let's see if this works. So the secant line here is going to be, secant line is going to be y minus the y coordinate, which is 0, equals the slope times x minus x coordinate, which is also 0. So the secant line always is going to look like the slope, which is 1 over the cubed root of x, I think. Hold on, I'm curious whether this is going to work and whether I can do it in my head. It doesn't, so let me do a slider for a. Why is it not letting me do this? Huh. There is a way to show this. Oh, it's because I forgot my x. So this is how our secant line behaves. All right. This is the secant line for these points being really far away. And the slope of the tangent line is the slope of the secant line as the points get closer together. Look at where these functions intersect. Now they're getting closer and closer together. The secant line's getting closer and closer to the tangent line. But notice that as this gets closer and closer to the tangent line, the slope of the secant line gets almost vertical. All right, and it's going to get really big. The slope of this line is going to get really, really big. And the slider function actually doesn't help that much. But like, as we get really close, to get really close, this is what our secant line becomes. Notice the secant line is just getting really, really close to infinity. Having a slope of infinity. Okay, so that's why there is no derivative here. Because we eventually get a vertical tangent line. And it's close to infinity, a slope of infinity from the right, and it's close to a slope of negative infinity from the left. And this is kind of a little extra visualization, but it's what's going on here. And that's the homework problems I wanted to go over. You can also ask me questions and work amongst yourselves as well. I love talking about this stuff, so I realize this was a big, long section, but there's some good material. This is the foundation for the entirety of this quarter. And foundation of differential calculus right here. Good luck and enjoy.